Guys, we are getting so close to the end, I can smell it, all right? And so we are going to take this idea of area that we have been talking about, and we are going to convert it into volumes. Okay, now we talked about volumes in geometry. We didn't make it to the 3D volumes whenever I taught it, whenever I had the students that I currently have while making this video. But you've seen them before, and we've seen them so far this year. For instance, if we had a right circular cylinder right here, we knew that the volume is going to be pi r squared times h. No big deal there. And all the way from middle school, anytime we had a rectangular box, we just did length times width times height of the box. And that told me what the volume was. And so those are all good, and those are some very basic ones. But not everything we find the volume of fits into this category where it's something that's a nice geometric figure, right? I think I am going to skip this slide and go straight to this one. Absolutely, yeah. So what if we have something, every time I see this, I think of like a fish or a slice of bread or something. But I always think of it as bread. What if I have this loaf of bread right here? Well, I still want to be able to take a cross-sectional area of it, as you see it's being done right here. So they kind of slice the bread right there. And ideally, if I can find the volume, or even if it's going to be so thin right here, that if I can just find the area of that slice of bread, and I sit there and do it all the way to the right and all the way to the left, and I add up all those areas, it should tell me what the volume of this whole loaf of bread is. Okay, so let's get a new definition of volume right here. Okay, we're going to have a solid S that lies between x equals A, which would be right here, and x equals B. So if I can take the cross-sectional area, if I can take this slice of bread right here and cross-sectional area S in the plane P of x through x and perpendicular to the x-axis, if that area turns out to be A, and A is a continuous function, what I can do is I can just do infinitely many slices of bread, add them up, multiply it by their thickness, all right? And of course we know that we can rewrite that. So yeah, this is the big key right here. In order to do volume, we are going to just be integrating from A to B this cross-sectional area times d of x. All right, so you've always been told that the volume of a sphere is 4/3 pi r cubed. Finally, here at the end of calculus, I'm ready to show you why. All right, so I'm going to put a 3D object on a two-dimensional plane because that's the best I can draw. I'm supposed to put dotted lines somewhere. I'm sure that would help. But suppose this is a sphere right here with radius r, and then I have x and y happening right here. Okay. Now, if I was to take the end of this triangle right here, and then just start spinning it around the axis, what I would get is this disc-shaped cross-sectional area. Okay. So let's talk about how everything relates. We know that x squared plus y squared is equal to r squared, right? And so if I solve this for either x or y, I'm just going to choose y. I get y is equal to the square root of r squared minus x squared. Okay. Now, I'm looking to find the cross-sectional area of this disk. There's another disk over here. I'm wanting to find the cross-sectional area of it. There's another disk right here. I'm wanting to find the cross-sectional area of this disk. There's another disk here. You can kind of see where this is going. Oops, that's supposed to be solid. I have all these disks that are lining up inside this sphere. It's really hard for me to show it on my whiteboard right here without you guys in the room, but I'm doing my best. But the idea is that all these blue disks are lining up from A until B. Okay, my endpoints. So I even have a little bitty disk right here at A. Shouldn't have used blue, but I have a little bitty disk right here at A that I'm going to want to find the cross-sectional area of. Now, in this case, since my sphere has a radius of r, that means that the distance out to B is going to be r, and the distance going out to A is going to be r as well. Well, since we're going to the left, let's call it negative r. So the cross-sectional area of just one of these disks right here is going to be pi r squared, right? Pi r squared. But it's this r is not the same r that we're dealing with when we talk about this r happening out here. I'm actually wanting the cross-sectional area of this disk. I am wanting what the radius of that disk is inside. Well, the radius of that disk has to be y units. So I'm going to take out that r, and I'm going to put y in its place. Because again, that is the radius of one of these disks. Let me do that again. So like this disk that's all over here on the very far left, if I was to find the radius of that disk, it would be this much. Okay? And so that distance right there is the variable y. Now, all of my disks are stacking in the x direction. So whenever I'm ready to find the volume now, I'm going to find the volume from negative r to positive r. And since they are all stacking along the x-axis right here, I want everything to be in terms of x. There'll be more on that later if that's confusing. So what does that mean? It means that I'm integrating from negative r to r. And then in order to find the area of one of these disks, let me just pull this out right here. That disk is just a circle. I know it looks like an oval right here because I tried to draw it three-dimensionally. But that disk right there is going to be a circle with this radius that's equal to y, right? Well, if y is equal to this, square root of r squared minus x squared, how I find the area of a circle is going to be pi times the radius squared. Well, that's just going to be pi times y squared. Well, that's just going to be pi times the square root of r squared minus x squared squared. And so whatever this comes out to be, I want to plug that in for my a of x. So pi times r squared minus x squared. Okay. The squared and the square root will cancel each other. Yes. Now we could use the fact that this is an even shape. Whatever's on the left side is equal to what's on the right side. Or we could just work it with this if you don't recognize it. I'm just going to go ahead and work it. So this will be a little bit different than my notes. So I could go ahead and pull a pi out in front. That might help. So that way I'm not dealing with that constant. And so I want to integrate what's in parentheses right here. Take the antiderivative of it. I'm doing my antiderivative step, so let me get rid of my integral. So this r squared, that'd be the same as 3 squared. That'd be the same as if I just integrated 9. If I integrate 9, I raise the exponent by 1, put it over the new exponent. If I integrate 9, it gives me 9x. If I integrate r squared, it gives me r squared x. And if I do the same thing with x squared, I get 1/3 x cubed. I'm evaluating this from r to negative r. Got the pi right there. I'm ready to plug this in. Okay, so I'm going to plug in r first. Well, that's going to give me r cubed. R cubed. And then if I plug in r right here, that's going to give me negative 1. Yeah, negative 1/3 r cubed. I'm going to subtract off. I'm going to plug in negative r. If I plug in negative r, I get r squared is r squared times a negative r cubed. If I plug in a negative r right here, ooh, I think it's going to change it to a positive 1/3 r cubed. Like I said, this is different than when I worked at my notes. I doubled it in my notes and just dealt with 0 to r. So I got a bunch of r cubes. Remember, my goal is to get 4/3 pi r cubed. So hopefully everything equals 4/3 on this. So I've got my pi. I know I'm going to have an r cubed. Let's see what happens whenever I add this up. So I have 1 minus 1/3. Just keep a running total here. I'm at 2/3. But I'm adding 1 to it. So that would be at 5/3. And then if I subtract a third off that, yep, happened. I got 4/3 pi r cubed. Therefore, that is why the volume of a sphere is 4/3 pi r cubed. Okay. Oh man, we made a mess of my screen. Hope it makes sense. If not, hit rewind, watch it again. Hopefully it'll make more sense the second time. If not, say, hey, work that example 1 again during the Q&A. Right? I'll be glad to do it. All right, let's go to some where they actually give me a function to work with. I think those will be more in line with what we're looking to deal with. Okay, so I like to have sketches on these. Okay, even though they don't ask for them, I like to go ahead and draw what's going on. It helps me kind of visualize what's going on better whenever I'm having to work this out. So it says find the volume of the solid obtained by rotating about the x-axis. So I'm going to be spinning this thing around the x-axis. The region under the curve y equals square root of x. There's my swoop. All right, and I'm only wanting to go from 0 to 1. Okay, so imagine taking this shape right here, this region. We can close it off if we want to. And we're just going to sit there and spin it around the x-axis. What do you think it's going to look like? Well, at the top, bottom's going to reflect down. And, remember, I'm not an art teacher, but yeah, it kind of looks like a bowl that's just sitting on sideways on the origin. So, again, the way I got that, I got my absolute value. Square root of x happening on both top and bottom because I sat there and spun it around the axis quickly. So what does that give me? How does that help me? Well, it gives me this cross-sectional area that I need. I can pull out that cross-sectional area, and the idea is, again, I'm going to have all these cross-sectional areas inside this bowl, and I want to take the area of all of them and add them up. And that should tell me what the volume of this bowl-looking thing is. Well, if I pull one of these out, I'm really interested still in what the radius is. Let's backtrack a little bit. I am finding the radius just from going from the middle up to here. I am finding the radius by just doing this height. That height is equal to y, which is equal to the square root of x. Okay, so that is what my radius is going to be. Well, what do I need the radius for? Because I'm wanting the area of, I'm wanting the cross-sectional area right here, and it's going to be a circle. It's going to be a disk, and it's always going to be pi times r squared. Well, if r is equal to y, and y is going to be the square root of x, my cross-sectional area, the area of just one of these disks inside this bowl right here, is going to be pi x. Now, in order to get what the volume would be, I'm going to take all of those disks that I have in here from 0 to 1, and I'm going to add them up. And so the area of each one is going to be pi x times the width of it, px, which is going to be really small. I'm here to tell you, you can always pull that pi out in front. Okay, so this pi can come out in front, and I can just integrate this x right here, which gives me 1/2 x squared. evaluated from 0 to 1. That's going to be pi. If I plug in 1 right there, I get 1/2. If I plug in 0, it goes away. And so the volume of this bowl right here is going to be pi over 2. The math of it isn't really hard. I really want you guys to focus on when you're working these problems. I really want you to focus on the setup, okay? And being able to draw everything out, find what your radius is. Let's go again. I'm going to change some stuff up a little bit. I don't think I'm going to have you work too many of these on your own. I want you to see as many examples as I have, because they tend to load. You will probably have 1 or 2 of these on your final from SEMA. All right, still finding the solid of the region that is bounded by, let's see, snake on a plane. I'm not going to need this part of it, so I'm just going to go ahead and just come up right there. Y equals 8. 1, 2, 3, 4, 5, 6, 7, 8. Let's call that 8 right there. Sound good? And x equals 0. X equals 0 is this vertical line. So I am looking for it's not the area of this region. What I'm going to do is I'm going to take that region and imagine spinning it around the y-axis this time. Just imagine that thing going crazy, spinning around the y-axis. What is my shape going to look like? Well, still going to have this bowl thing coming up, but if I spin that around the axis, it's also over here. And so I drew this really big for some reason. Yeah, I still have the bowl. It's hard to avoid having a bowl on this. And so what I'm going to do is I'm just going to draw a typical cross section on this. And so, yeah, I still have a disk. I still have a circle when I pull that out. And the radius is going to be this distance from the center out to the edge, meaning that the radius is going to go from here out to the edge. That's my radius. Keep that in mind. We have some differences on this one, though. Okay? And so my radius, yes, it is this distance x right here. But since all of my disks this time are going to stack up and go in the y direction, I want to integrate everything with respect to y this time. Anytime I spin it about the y-axis, I want to integrate it with respect to y. Okay, so what does that mean? Well, still finding the volume. And my upper and lower limits of integration is going to be where my first disk starts at. Well, it's on the y-axis, so the first disk is at 0. And I have all these disks going up until the very top, where that green line was. That green line's still here, and it is at 8. At 8 up here, I'm going to have my last disk going around. Okay, so there's where that 8 comes in. And then I want to throw my cross-sectional area in right here. Well, my cross-sectional area is going to be pi times the radius squared. Well, the radius is x squared. But I want stuff in terms of y. So I need to change this. X is going to equal the cube root of y. So while, yes, I agree that this distance right here is x, I also agree that it's the cube root of y. That's going to be that distance in terms of y. And so I get the cube root of y squared times pi. So I still have my pi r squared working in there. Got some rewriting to do on this. So I'm going to go ahead and pull that pi out in front. I just like it out there in front. And this is going to be y to the 2/3 dy. So I'm ready to integrate. So raise the exponent by 1, so that's going to be 5/3. So 3/5 y to the 5/3 going from 0 to 8. Ooh, 0 is going to go away. If I plug in 8, I should get like 96. I love exact answers on here. So the volume of this giant bowl right here is going to be 96 pi over 5. Now, unfortunately, we're not always going to have a disk. There's one more shape that will come up that I want to talk about before I end this video. And that other shape is going to be revealed in this example. So, still have a region right here. Let's see how this one's going to be a little bit different, what our new shape's going to be. So I have y equals x. Well, y equals x is just the identity function. Let's demonstrate it that way. And y equals x squared. Y equals x squared should come down like so. And so what I want to do is I want to take the region that is being bounded right here, and I want to rotate it about the x-axis. Remember, x-axis means I'm going to do everything with respect to x on that, so we don't have to worry about switching it to y's. We'll switch another one to y's in just a little bit. So I'm going to redo my whole drawing down here, except for this time I'm going to rotate it. So imagine spinning this thing around the x-axis. Okay, I've got this enclosed region. I'm going to blow it up just a little bit so you can kind of see it better. I'm not too impressed with that. I'll blow it up a little bit so you can see it better. There we go. I like that one better. And so that region, if I was to spin it around this x-axis, it's going to reflect down like so. So my shape isn't going to be a full bowl this time. If I was to cut this coming straight down right here, what I would get for its cross-sectional region would be, see what that is? Now, if you're hungry, you can go ahead and call it a donut. That would be fine. I am pretty hungry. I haven't eaten in a while. So I'm going to call it a washer. You're going to hear me refer to it as a washer. And that's the second shape that we can have on this, is a washer. Okay, now, whenever I'm looking to find the cross-sectional area, think about a metal washer right here. It's just going to have area around the side. Or think of a donut, all right? We don't eat the whole of a donut because it's nothing but air right there. We eat the ring of the donut. And so whenever I'm going to find the area of this washer, what I'm going to do is I'm going to go ahead and act like it's a full circle. I'm going to find this radius right here. All right? I'm going to go ahead and call it R2. I might switch that notation later. And then what I'm going to do is, so that works the same as if I was to find the area of the whole thing, okay, including this middle section right here. But I don't want the area of that middle section. There's a hole right there. So I'm going to subtract off this little bitty radius right here. I'm going to call it R1. Okay. So what my cross-sectional area will look like each time that I have a washer is it's going to be pi times my big radius squared minus pi times my little radius squared. I have some redundancy there, so I could pull out that pi, and this is going to be the formula I want to plug into. You might be asking, well, what's the radius? How do I find out what the radius is? Well, remember where this came from. The radius is going to be the R2. That's going to be the line all the way up to this red one, all right? All the way up to my straight line right here. And so that distance right there is going to be y, which in this case just happens to equal x. Okay. So I get pi times x squared minus my little radius. My little radius is just this little bitty distance that goes up to the bottom of this curved line. It's just this distance right here. Well, that's still a vertical distance y, In this case, it's equal to x squared. And so if I plug in x squared for this radius, I get x squared. So you're just subtracting two circles from one another. And so that's really the only new part if I have a washer. Okay, I can still pull my pi out in front. I have all of these little washers stacking up from 0 until, this is the point 1, 1 right here. So from 0 until 1, and I just bring up my cross-sectional area. X squared minus x to the fourth dx. And again, the dx is there for the width of each washer, which is not going to be very much. So I'm ready to integrate. 1/3 x cubed minus 1/5 x to the fifth. Evaluate it from 0 to 1. I love plugging in 0. That's going to be easy. So whatever I get, just got to subtract 0 from it. So I got 2 pi over 15. And that'd be my answer. So the volume of this is kind of got a hole right here in the middle, but the volume of this shape would be 2 pi over 15. Now you're probably thinking to yourself, Mr. Lovely, okay, you have made this as hard as you can make it. If you want to, this would be a good spot to hit pause on the video, go get yourself a donut, and then finish up the rest of this tomorrow, because I'm sure you're going to have plenty of time to get through this week. And that's a pretty good chunk right there. But there's a couple more problems I want to show you on the back half of this video. So if you want to, go ahead and hit pause, go get something to eat, take yourself a break. Now's a good time to do it. That's normally where I would have stopped class for the day. But I'm wanting to get everything done in one video. So I'm going to keep going. Man, my erase all is not happening lately. All right. You guys see where the kicker is going to be on this one? How this one's going to be a little bit tougher? Okay, so looks like we have the same lines. Y equals x, y equals x squared. I should have erased all of it. I'm thinking. So we still have y equals x and y equals x squared. So something like that. I'll try to get it so it's just right. But this time, I am rotating this region not about an axis, but about y equals 2. Ooh, maybe I need to move this a little bit. Y equals 2. I'm gonna move my x-axis down a little bit. Never mind that it's not straight. So I'm taking this region. So this comes up to the point 1 right here. So this would be 2, 3, 4. I'm wanting to rotate it about this imaginary line right here. Well, that means that, just imagine it rotating up. Got to do a little bit of abstract drawing here. I think it's going to look something like so. Does that look right? So I get a great big washer on this one. There's my outer radius, and there's my inner one. Okay. And so if I pull this out, I still have a washer. It's just a lot bigger. It's got a bigger hole in the middle of it. And so imagine again, though, I'm stacking all these washers up going in the x direction. Okay, going from left to right, going from 0 until 1. Okay. And so that's still going to be what I integrate from. So I got my pi, and I'm going from 0 to 1. Now remember what we have in here on the inside. We have my outside radius squared minus my inside radius squared. So that's what I have to find right here. So what I need is, I need the distance from the center all the way up to the top of this washer. From the center right here all the way to the top of the washer, all the way to that curved line. Well, normally that distance, I can also come down with it. That might be easier. I can go from the center all the way down to this curved line right here. That is going to be easier because normally this distance coming all the way down is going to be 2, correct? But I did not come all the way down to the axis. I left a little bit of a gap right here that I didn't account for. Well, that gap is going to be y equals x squared. So my outside radius is going to be 2 minus x squared squared. Pi times that. Again, I got that because this distance all the way down to the axis is 2, because that's what I rotated about. But I didn't come all the way down to the axis. I have this little bitty gap right here that I shorted myself coming down all the way to the axis. So if I subtract off that gap, which happens to be one of my functions, I get my outside radius. Now I'm wanting to subtract off my inside radius. I'm going to use the same idea on this. I got stuff happening everywhere. I'm going to try not to erase it though. But I still have, look at my inside radius on this original one right here. Okay? It's going to be this distance that comes down to right there. Okay? Same distance right here. And so I'm still going to use the fact that this distance coming all the way down is 2. And then subtract off this vertical distance right here, which just happens to be y equals x. So this red arrow right here corresponds to this red arrow right here. I got red arrows everywhere. And normally it would come, if it came all the way down to the x-axis, that distance would be 2. But it doesn't, all right? It shorts itself right here, and that distance is going to be y, which equals x. Okay, one of my functions is going to be up there on top. So for that reason, I had 2, but I shorted myself x units. And that's a lot easier to describe whenever you're here. So I pulled this pi out in front, so I'm good there. And so right here I'm going to have, let's see, 2 minus x squared squared. And back here I'm going to have 2 minus x squared. And again, that came straight from my cross-sectional area. Oh, I'm not ready to integrate yet. I don't want to deal with those powers in there. So I'm going to go ahead and expand this out. I got 4 minus 4x squared plus x squared. Might check my math on that. And I'm going to expand this out and distribute a negative at the same time. Hold your applause. I get 4 plus 4x. That'd be a minus x squared. Got some like terms to combine. I'm wanting my integration to be as simple as possible. Well, lucky for me, oh man, I messed up. I hope you didn't applaud me. This guy should be a 4. Obviously, if I square x squared, I get x to the 4th. So, I got the x to the 4th. He doesn't have anybody to play with. I got a negative 4x squared and a negative x squared. That's going to be negative 5x squared. My 4's do cancel. 4 minus 4. Thanks for playing our game. You're out of here. And I just have this plus 4x to bring down. So much easier integration than dealing with those binomial squares up there at the top. I'm going to erase this so I have room to work it. And so if I integrate this, let's see, that should give me 1/5 x to the 5th minus 5/3 x cubed plus 2x squared, right? 4x squared over 2, 2x squared. And that'll go from 0 to 1. Again, I love the fact that I have 0 in there. Enjoy it while you got it. If I plug in 1, I get 1/5 minus 5/3 plus 2. And so that gave me like 8 pi over 15. Whew, man, a lot of work right there. A lot of work. Okay. All right, I've got one more of these I want to show you, but I just want to review a little bit with you before I show you the last one. I think I have a review in my notes. Hopefully, I put it on here as well. So I want to show you that there are two different ways that this can come out. If I'm dealing with slides or solids of revolution, okay? And so remember, I can obtain these, all these solids of revolution I am obtaining by revolving a region about a line. As you saw in the last example, we really hope that line is the x or y axis, and it will be a lot of the times, but there's going to be a couple of them where it might be the line y equals 2 like we had on the last one, okay? Now, I like it when the cross section is a disk, we found out, okay? And so remember how we did this. What we're going to do is we are going to find the radius in terms of x or y. Remember, it's going to be x if all my disks are stacking in the x direction. It's going to be y if all of my disks are stacking on top of one another. And we simply use the area to be pi times the single radius I have squared. Okay. Now for if the cross section turns out to be a washer or a donut like we talked about this morning since we're hungry, a lot of it's the same except for my area is going to be pi times my outer, is there two t's in outer? Outer, I don't know, radius squared minus pi times my inner radius squared. And that was the idea behind it. Okay, so you just treat it as two different disks that are stacked up on top of one another, and you just subtract them, and that gives you that middle cutout. Okay. So let's go full blast. However hard we can make this. It's coming up right here. Okay. So I'm going to make it so it's not about an axis, and I'm going to make it so that we are stacking them up in the y direction. So we have to switch everything in terms of y. I've got my same region. So I don't know why I keep erasing it. Should have looked ahead a little bit more. I have this region right here. But this time I am rotating it about the line x equals -1. I'm going to redraw this. My region right here. And so if this is 1 right here, then probably about right here is 1. I'm wanting to rotate it about this line. Well, that means on the other side of the rotation it's going to pick up at 3 and go to 4. So, and I don't know why I can't draw pictures that are the same size. It really baffles me. Right, give me another go at that. Close enough. All right, close enough. Now, I always like to draw myself an example as to what's going on. Okay, so if I'm rotating about this way, that means that my washers are all going to be stacking up, going up and down in the y direction. All right, so what I'm wanting to do is I'm going to bring this washer out, and I'm wanting to find its cross-sectional area. Okay, and so what it said I had to do, it's going to be in terms of y, isn't it? Good to know. It's going to be in terms of y, because that's the direction they're stacking. They're stacking the same direction that the y-axis is going. So I've got my pi times my outer radius squared minus pi times my inner radius squared. Let's talk about how to get my hands on the outer radius. The outer radius is going to go from here out, all right? up here in my picture, that is from right here all the way to this curved line, would be my outer radius. So, again, I'm going to just kind of show you how to do. There's formulas for this. YouTube them if you're more of a formula-driven person. But I know this distance right here is 1. And I'm adding to it this distance that I'm going in the x direction. Remember, I don't want x's in this case. I want y. So that curved line came from right here. The square root of y is equal to x. And so instead of the x, I want it in terms of y. So I got 1 plus the square root of y for my outside radius. Now my inside radius, I'm going to do it in red. Okay, my inside radius is just this little bitty distance right here. On my picture, my inside radius is going to be this distance, oops, to right here. All right, so I still have my 1, and I'm adding this small x distance right here. Well, that's on a straight line where y is equal to x. So that would just be 1 plus y for my inside radius. I hope that makes sense. I don't have you guys here to kind of gauge your faces to see if I need to explain it differently. So rewind it, watch it again. But that's the hard part, I think. Okay. From here, we can clean up everything down here if we want to. I can pull out my pi. I can expand this binomial. Let's see if I can do it right this time. 2 square roots of y plus y. And then I'm going to expand this binomial and distribute the negative at the same time. Let's see if I can do it right this time. So I get a negative 1 minus 2y minus y squared. And feel free to clean that up from here if you want to. Okay, I'm going to kind of do it in shifts up here. I'm going to go ahead and find my volume. Again, my volume is going to be from 0 to 1. It's not always going to be from 0 to 1, but let me explain one more time why it's going from 0 to 1. Because my bottom washer is going to be stacked down here it's going to start at 0, and my very top one is going to come up to the y value of 1. So that's why I'm going from 0 to 1. Okay. I'm going to go ahead and pull that pi out in front. And as my Calc 3 professor would say, lo and behold, your 1 and negative 1 cancel. All right, so we don't need that in there. What else we got? So we have 2 square roots of y left. It should have a negative y, so 1 minus 2y is a negative y. And I got the y squared, the negative y squared, no one wants to play with, so we'll leave it. So kind of tough on this one, the fact that we're having to deal with y's again, so we'll need some practice. See, this is just 2y to the 1/2. So if I raise the exponent by 1, that's going to be 3/2. Divide by 3/2 will give me a 4/3 out in front. A negative 1/2 y squared and a negative 1/3 y cubed. Back here. Lucked out once again with the 0, so yeah, I just need to do 4/3 minus 1/2 minus 1/3, and that gives me a nice pi over 2. And so the volume of that big, kind of empty it looks like, whatever that shape would be, is going to be pi over 2. Over the years, I've skipped around in the notes a little bit as to what I cover and what I don't cover. Good. All right. I'm glad I skipped that. I was going to skip it this year anyway. One more I want to talk about that you'll see. And I want to go back to the shapes. Like we did sphere at the beginning, I want to go ahead and do a pyramid here at the end. All right? So, I'm finding the volume of a pyramid whose base is a square with side L and height h. It works better if I can put this on a coordinate plane. And there's a couple different ways I can throw this on a coordinate plane. I am going to work it this way. And remember, I am not I am unfortunately not an art teacher, so I am trying my best. We had Miss Monroe up here. I'm sure she'd be able to help out a little bit more. Ooh, I'm doing good so far. I hope I don't blow it. So that means that there is an imaginary line back here that you don't see until right there. That's the crease of the pyramid. Okay? Now, I did good other than the fact that the base is a square. All right? So you're just going to have to think three-dimensionally on this. It looks like a rectangle, but this base is going to be a square, and one side of it's going to be an L. And then the height of this pyramid, the height of the pyramid coming all the way down to its base is going to be h units. Now remember, the theme of today is that we're wanting to cut out a slice of this, and oh boy, we're wanting to cut out a slice of this, and so that we can find what the cross-sectional area is of this one slice, and then add it up all the way from top to bottom. Well, the length of this edge is not going to be L, so I'm just going to call it S. And luckily it's a square still, remember, because the base is a square, so every cross-sectional area coming through is going to have to be a square, so it's going to be an S by S. Now from here I'm going to use the fact that it's a pyramid, and I'm going to set up a ratio. Okay, so wherever this landed coming down my axis, let's just say that it's x units down. That's my variable of how far I've come down, x. Okay, and so the height of that small pyramid is what we're going to use. So the height of this small period is x, and then the height of the big pyramid is the h. So I'm going height to height is equal to the length of a side of the small square in the middle is an S, while a length of the side down here on the base is going to be L. And remember, my goal with this is to figure out what the area is of this square. All right, to figure out what the area is, I'm going to do side times side, so I need all this in terms of side. So I'm not going to cross multiply here, even though it might look like it. I'm actually going to multiply both sides by LH. Okay? And so whenever I do that, that gives me SH is equal to XL. Solving this for S, which is what I need. You don't see why I need S, just hold on tight for a second. I get XL over H. Making it so my cross-sectional area now, which was side squared, is now going to be, I'll just square this side as well. So it's going to be, I'm going to rewrite it a little bit. XLH squared, which will just be squaring everything that I have here. Squared all of it in order to square the S. So I'm ready for my cross-sectional area. Okay, I want to add them all up to find my volume. I don't have a pi going through on this one because I don't have a disc or a washer. Okay, so, but I know that I'm going to have all these different cross-sectional areas in here that are starting back here at 0 and going all the way to h. So 0 to h is going to be my upper and lower limits of integration. And then from there, it's just going to be, bring up my cross-sectional area. So L squared over H squared X squared. Okay? And this is going to be in terms of X. Since it's in terms of X, I could bring this out in front of my integration. I have L squared over H squared, and all I have to do is integrate the X squared, which gives me 1/3 X cubed, evaluated from 0 to H. L and H in this case are constants, okay, and that's why I could bring that out in front. So what we have going on here? Oh, I got to plug in H. And so, got my constants times H cubed over 3. If I plug in 0, everything is going to 0 out. It's an ongoing theme today. So both of these h's cancel with 2 of these, and I get my final answer. So the volume of this pyramid is going to be the length of the base times, or squared, times the height divided by 30. We have one more video left. We're going to be looking at how to find volume a little bit differently. Sometimes it's easier, sometimes it's harder, but here's some problems for you to work on for the rest of the week.